Hi, my name is Samir Desai, and in this video, we'll learn how a change in pressure can cause a system in equilibrium to shift.
Le Chatelier's principle is frequently parallel to homeostasis. When a stress is placed on a system, the system will counteract the stress by shifting its equilibrium. As we previously discussed, a common disturbance to a system is a change in concentration. To determine how a reaction will shift with a change in concentration, we compare the equilibrium constant, Keq, with the reaction quotient, Q. Keq is a constant whose value is determined when the reaction is in equilibrium, and therefore will not be affected by a change in pressure. But the reaction quotient, where Q is equal to the concentration of the products over the concentration of the reactants, will be affected by things like pressure, concentration, and temperature. It's easy to see how a change in the concentration can affect the value of Q. For example, you can increase the concentration of the products, making the numerator larger, increasing the value of Q. Seeing how a change in pressure affects the reaction quotient may not be as obvious. To understand why pressure affects the reaction quotient, let's incorporate the ideal gas law into the equation. The ideal gas law, PV equals nRT, can be manipulated to isolate pressure to give us P equals nRT over V. Keep in mind that concentration, seen in the reaction quotient, is in molarity. Molarity is the same as moles per liter, which can also be described by N over V. So a change in pressure, let's say a decrease in pressure, will increase the volume. This causes an overall decrease in molarity, which ends up affecting the value of Q. So a change in pressure, and therefore a change in volume, may also affect the molarity, which will change the value of Q. Now, while we can determine Keq using the concentration of products over the concentration of reactants, this can also be written in terms of partial pressure, where Kp equals the partial pressure of the products over the partial pressure of the reactants. Suppose we have 2 moles of gaseous product for every 1 mole of gaseous reactant, then our Kp would look like this. Now, if we were to change the total pressure, let's say we were to double the pressure of the system, and it went from 1 to 2, then our partial pressure would also change, and the reaction quotient would be Qp equals 4 times the partial pressure of the products squared over 2 times the reactant pressure. When we compare the equilibrium constant to the reaction quotient, doubling the pressure leads to Qp doubling in relation to Kp. Therefore, Qp is greater than Kp. Comparing these values tells us that the reaction will shift to the reactants. And a quick way to remember this is by drawing a line to make an arrow with the greater than less than symbol. It creates a left arrow, which confirms the reaction will shift towards the reactants. Keep in mind that the expression for partial pressure requires at least one reactant or product to be a gas. If there are no gases, then a change in pressure would not cause any shift in the equilibrium. Similarly, if there are gases on both sides of the reaction, the moles of gas on the reactant side must differ from the moles of gas on the product side. Otherwise, the change in pressure would not cause a shift in the equilibrium. That said, if there is at least one gas in the reaction, and both sides don't have equivalent moles of gases, these two rules will allow you to predict the shift without having to compare the equilibrium constant and reaction quotient. If we increase the pressure, the reaction will shift to the side with fewer moles of gas. And if we decrease the pressure, the reaction will shift to the side with more moles of gas. Let's use this information to predict how a reaction will shift when pressure is changed. This question contains 2 parts. 1, which reactions will be affected by an increase in pressure? And 2, which way would the equilibrium shift if it is affected by pressure? To answer the first part, remember there are 2 criteria that must be met for a change in pressure to affect equilibrium. 1, the reaction must have at least one gaseous reactant or product. And 2, the sum of the stoichiometric coefficients for gaseous reactants and products must be different. Starting with A, we see this reaction contains gases. There are 1 plus 3 moles of gas on the reactant side, and there are 2 moles on the product side. So both sides certainly have different moles of gas. Therefore, this reaction will be affected by an increase in pressure. As we learned from the previous slide, an increase in pressure will shift the reaction to the side with fewer moles of gas. 4 moles on the right and 2 moles on the left, so the reaction would shift right toward the product. To understand why it shifts toward the product, let's write out the equilibrium constant and reaction quotient equations. Kp equals the partial pressure of NH3 squared over the partial pressure of N2 times the partial pressure of H2 cubed. The question asks about an increase in pressure. Let's say we double the pressure. Then Qp equals 2 times the partial pressure of NH3 squared over 2 times the partial pressure of N2 times 2 times the partial pressure of H2 cubed. This gives us 4 over 2 times 8, all times the equation of Kp. Now, what is the relationship of Kp to Qp? Qp is 4/16 or 1/4 the value of Kp, meaning that Kp is greater than Qp. Let's draw a line to create an arrow. When Kp is greater than Qp, the reaction will shift to the right, towards the product. Moving on to B, again, this reaction has at least one gaseous reactant or product. In fact, it has 2 moles on the reactant side, and 1 plus 2 moles on the product side. Again, the equilibrium will shift due to an increase in pressure, and it will shift left, to the side with fewer moles of gas. Therefore, it will shift towards the reactant. In C, we can see both the products and reactants contain gases. The reactants contain 1 plus 1 mole, or 2 moles, and the product also contains 2 moles of gas. The coefficients must be different for pressure to affect equilibrium. In this reaction, there would be no shift. Lastly, D. We see solids, liquids, and aqueous solutions, but there are no gases on the reactant or product side. So pressure will not affect the reaction, and there would be no shift in equilibrium. So there we have it. Predicting how a change in pressure will shift equilibrium is heavily reliant on observing the gases, and is just one more component in understanding Le Chatelier's principle.